As we've seen, the force F12 with vector components F12x and F12y is completely indistinguishable from the action of those two forces at a given point. In other words, if we make measurements at this point and we don't know whether F12x and F12y are acting together or F12 is acting by itself, we can't tell the difference. We cannot measure anything at this point that will reveal a difference. So we're pretty confident that this is the case, and we're going to verify this within a certain level of uncertainty. Okay, we can't verify it to 5 significant figures in our lab. Maybe we could actually, but we're not going to get 8, for example. Okay, this is well verified, and everything in physics is consistent with this equivalence. Okay, well, anyhow, so we got our forces F12 and F13 acting at a point. Now, we're going to simply say that this is equivalent to, and this is the mathematical symbol for equivalence. Now, it really doesn't apply to pictures. It applies to equations and mathematical expressions. But if the pictures embody a mathematical expression, it says the mathematical expression that's equivalent to this picture is equivalent to the mathematical expression that's equivalent to this picture. So these two are in fact equivalent. So I'm not stretching the notation too far. Okay, well, all I'm asserting here then is that if instead of F12 we have its two components acting at this point, and if instead of F13 we have its two components acting at the point, the situation is indistinguishable. The action of these forces is completely equivalent to the action of these forces. Now, if we consider just the two forces acting in the x direction, they're acting, in this case, in opposite directions. The forces in the y direction are, of course, acting in the same direction. So, in this case, in the case of the x direction, this force is fighting this force. This force is pulling this way, that force is pushing that way. Okay, well, if we sketch the two vectors, the way vectors are sketched, head to tail, to show how they combine, we see an indication that this vector is acting in this direction. This vector then acts back in this direction, giving us a vector in the same direction. And we're going to let this red vector be the sum of these two vectors. And the idea there is very intuitively obvious. If the two vectors are acting along the same line, then the direction of the resulting vector is going to be along the same line. If I'm pulling back this way and you're pulling that way, directly opposite me, both in the same direction, the direction that we'll designate as our x direction, then the net force that's felt at the middle is going to be less than the force you're exerting and less in magnitude than the force I'm exerting. And if the forces look like this, that's what we're going to have. And of course, we can calculate that by adding the 8.0 newtons of this force to the negative 4.3 newtons of this force. I'm not including the numbers, I just want to do a picture right now. I'm going to sketch the picture for the y direction, and you should sketch that yourself and compare, and then we'll go ahead and put everything together. So here I have my F12y vector, initial point here, terminal point here, then my F13y vector from here to here. That vector should have been a little bit longer, I think. This one seems about right. So it's not drawn very well to scale, but the vectors intuitively are in the same direction. So their magnitudes are going to add and so forth. And the vector that we get as a result of these two, me pulling in this direction with this force and you pulling with this force, adds up to this force. And now we simply put this force here together with this force here, and we are going to be able to get the resultant force. Now I label this force F total X, F total Y component, and I put them together because these two forces acting at the same point are going to give us the same result as or the identical effect to the resultant force at that point. And as a result, we can sketch this parallelogram, which is in this case a rectangle. And our F total force. Now again, we know that vectors add this way because many experiments have confirmed this to great precision. And we know that at least to great precision this appears to be the case, and we make the conjecture and we act as if the conjecture is correct, the conjecture being that that is the way forces act to any number of significant figures. Okay, notwithstanding possible graininess of space and so forth. We won't worry about that right now. So we can draw the same picture, but we can add this F total force up here, not a very straight line. And of course that corresponds to what we get if we complete a parallelogram up here and go from our initial point to the opposite diagonal of the parallelogram. Okay, and I haven't proved all those connections, all the trigonometry, but it's just basically high school trigonometry and not very advanced high school trigonometry to prove this, just a little trigonometry, little geometry. Now I've added the labelings of the vectors. I put the actual quantities, 8.0 newtons times I for F12x, 8.9 newtons J for F12y, and the components for F13, and I've labeled them here for the most part. It looks like I missed one. Let me put that in. I had missed the F13x, and it looks like I missed the F12x as well. I'll just label that one, 8.0 newtons times I. So 8 newtons times I, negative 3.7 newtons times I, adds up to 8.0 newtons times I, plus a negative 4.3 newtons times J, and I've got wrong numbers there. Let me fix it. Okay, this should have been negative 4.3 newtons times I. Anyhow, I've got the calculation of X total and the Y total forces, just adding the J components here, adding the I components here, and I've then labeled the total Y component here and the total X component here, and then the net force, and I've got the components, 3.7 newtons times I, 15 newtons times J, just the same calculations we've already seen, and representing that as 15 newtons, negative 3.7 newtons vector. And I've added that label up here. So we constructed a graphical picture to show how this is done, and then we put the numbers on it and completed it numerically, obtaining our net force resulting from these two forces. Now there's a question, how could we measure this force? Okay, how do we measure this force on this point? Well, the most common way to measure that, there are various ways we can measure how much it accelerates a given mass. We can do all kinds of things, but the static way of doing that is generally to measure the force that balances these two. We call this the equilibrant force, or the balancing force. I'm going to call that the equilibrant force. Balances the effect of these two forces, so the net force at this point is 0. So I'm going to write a couple of comments there and then continue. Okay, so I labeled this F equilibrant, and the equilibrant force, F equilibrant, has a property that it balances the combined effect of F12 and F13, in the sense that at the common point here, the point at which all these forces act, the net force is 0. Okay? When this balances these forces, then you get 0 net force here. And it's fairly easy to tell in many cases if you've got 0 net force. Like if they all apply to something on which no other forces act, then that something doesn't move, doesn't accelerate. Okay? There's no change in the motion. And let's not get into that right now. Just doing this in an intuitive way. If they all apply to something that's initially stationary, it will stay stationary. Let's put it that way. Okay, as usual, I'm cramming things onto the board until it chokes. But now, if F equilibrant balances F1 and F2, so if the net force of F12 and F13 and F equilibrant is 0, then F equilibrant plus F total being in every respect equivalent to the action of F12 and F13, is going to have to add up. F equilibrant and F total is going to have to add up to 0 force, which is equivalent to saying that F equilibrant is the negative of F total, which will be then negative 3.7 newtons times I minus 15.0 newtons times J. And that could be written in ordered pair form. I crammed that in here. Negative 3.7 newtons, negative 15.0 newtons with an arrow over it.